Hi everyone, welcome to the second session related to the Radio RAN protocol stacks, where we are covering in details all the related aspects, especially for the functions for each layer in details with good visualization examples. And also we have covered all the related parameters. In the first session, we have went through the details of, in general, high level about the user plane architecture, and we went through how the call or the data flow is going to fly or transfer from the end-to-end perspective. And if you remember, we covered RLC in details, and we covered all the related parameters to RLC with some other good information. In case if you didn't watch this one, you can go through the playlist of the Radio RAN protocol stack to watch the session one before going to this one. In today's video, we are going to cover the BDCP part, and we'll give like the details of the BDCP functionality in details with good visualization example as well, and we will highlight some of the interaction of the TCP. This will be the second session. In the next session, I will give a high-level introduction about the TCP as well, to fully understand the interaction between all the layers, including the TCP. And the last one will be covering the MAC. So in total, we'll have a full session. So now let's move forward, see what you have today. So this is like an overview of what we're going to cover today. If you look into here, we have the first part we're going to cover. It's about the BDCP function in general. And we'll just give first high-level introduction, then we'll go deep dive for each function, and ending by I will be just going through the BDCP variables as we did for the RLC last time. And this TCP, this will be the next session. Next session will be covering the TCP function, and also the last one here will be included in the third session, which is TCP versus BDCP and RLC related parameter relation. But also we'll be covering that part today in high level. And in the top right here, if you look into the top right here, this is the parameters where we are going to cover it today. So let's move forward to see what we have. So again, I like first to go through the high level before jumping into the details for each and every single parameter or function of the BCP in details. So as I have done in the last session, I like first to cover the BDCP header as you look into the left side here. But the BDCP header is more simple compared to what we have discussed for RLC. It's having much less content compared to the RLC. So first of all, you need to understand the header, because the header will make it very clear whenever you go deep dive for any even signaling analysis, or even when you try to understand the function of any of the BDCP layer or TCP or RLC or even MAC. So the left figure here, if you look into here, it's similar to the RLC. This is you will find in the header usually, like if you are opening Wireshark, you will find, for example, DC or D or C, and this is exactly same as RLC. DC, this like if it's the value is 0, this means this is a control video, means it's asking, for example, for signaling acknowledgement. While it's one is data video. And our main focus today will be about the data video. And this is our just reserved for future use. It's not using for anything. The most important is a BDCP sequence number. BDCP sequence number is having similar functionality compared to the RLC sequence number, and sequence number in general is being used to be able for from the layer itself to be able to track the packets, or the sequence number associated to the packets. So the layer will be able to track this packet in case if it's like received out of sequence from the receiver, it will understand based on sequence number. It can make a retransmission based on sequence number, reordering based on sequence number. So sequence number is very important, especially for the for retransmission point of view, and if in case if you have any packet loss. And the third one is data, and you have this MAC-I. This MAC-I actually is used for the integrity and ciphering. It's like a kind of values being added for use for integrity protection and ciphering, and this is optional for the data radio bearer. It's not must, it's optional. It can be configured, can be like enabled or disabled for data radio bearer, but it's must signal radio bearer. So this is like the overview for the BDCP header. And again, the sequence number can be exactly same as RLC, 12 or 18 bits. And this is also the window size. If you don't remember window size, you can go back to the first session. And here, this is just a high level, like about the functions which can be presented. We'll go through each one of them in next slides. So let's move next slide and see what we have. So here, I just quoted in the left figure here, the figure from the 3GPP and also the function. Then the bottom left here, if you can see the bottom left, and the top left here, this is the function of the transmitter and receiver. And if you look into here, it will find that it's exactly the same. At the first part, at the first function of the BDCB, which is must, this is must be done from the transmitter side. You'll find that the transmitter usually having something called transmission buffer and sequence number allocation. This means that first thing the transmitter will do once it's received the packet from the upper layer, which is the TCP or coming from application moving to CB, IB, then it reaches to BDCB. The first thing will be done from the BDCP layer. It will be assigning a sequence number again to be able to track this packet, and also it will help the receiver to do this kind of reordering and so on. So this is the first thing. And there is something called transmission buffer. Once the packet arrives to the BDCP buffer, it will start a related timer called a discard timer. We'll be discussing that part in details in the next slides, but this is just the first thing that the BDCP will do. The second part, which is optional, it's not must, it's header compression. The first one is must be done. Second one is optional. It's header compression based on robust header compression, and header compression can be done to reduce the packet size. And reducing the packet size in general, especially if you reduce the IB header, reducing the packet size in general can bring like a better capacity, and also can sometimes improve your blocker rate, because you can have more energy per bits if you reduce the size of the packet. This also will be discussed in details. And the right figure here, if you look into the header compression, you have a different profiles, and I will be showing how to check this from the drive test. This can be enabled based on the vendor. It can decide which profile to like to enable. Usually, the header compression is being used for the voice data, like for example voice over NAR or VoLTE. But if you're speaking about 5G, it will be voice over NAR. So voice over NAR, for example, it will be highlighting for profile 1 and 2. So if you found from the drive test profile 1 2 is enabled, this means you have header compression for the voice over NAR. And you can also do it for TCP IP and also other multiple profiles here, and this is again depend on the vendor side. Then moving to the next two parts, will be just highlighting in like here. I will not go through them in details. Integrity, protection, something. This is very easy, but all the others will be going in details with live visualization example. You have integrity protection and ciphering, and this is, if you remember in the header, we mentioned something called MAC-I. In general, the integrity protection and ciphering is done by the receiver and transmitter, with like a communication done between both of them, and the receiver uses the integrity protection key, for example, to verify packet authenticity and to prevent, for example, RAG insertions or like any attack or something like that. And the integrity and ciphering in general, both is mandatory for signal radio bearer 1 and signal radio bearer 2. This is like always on. It cannot be disabled, okay? But it's optional for data radio bearer, DRB, okay? While this is the integrity job, the receiver is using that part to verify the packet authenticity. While the ciphering actually is used to improve the security in general, and this is by helping to ensure that only the intended of the reception is able to interpret the data. Like only the receiver, which I'm directing the data from, will be able to read this kind of data. Any other devices cannot do that. Only the intended device. So this is the main idea of integrity protection and ciphering. Okay. Header will be adding in general. Then after moving forward here, you will have this kind of number 5, which is split bearer or routing or duplication. And this is usually happening mainly in the non-standalone. If you have a non-standalone and you decided to do a bearer split through transferring data from for example, if you speak about option 3x, so you would like to transfer data from 5G to 4G through the X2 interface. We'll go through the details of that part for all these 3 points. And the last part, and the most important as well, related to reordering, and this is the reordering and in order delivery, mainly done at the receiver side. This is mainly done at the receiver side, and there is a parameters to control all of that. And also, we're speaking about something called the BDCB retransmission, how the BDCB in general is doing retransmission. If you remember last time, I highlighted that retransmission can be done by this TCP, can be done by BDCB, RLC, and MAC as well. But the BDCB is kind of different compared to the others because it's not retransmitting a specific packet. We'll go through the details for each of these points in next slides. Now let's go through one of these functions one by one to cover it in details to give you much better understanding about it. Before going to the last each of those functions, if you look into just try to code the table on the left, this is actually the parameters where you are going to find it in the 3G layer 3 messages. Like this is kind of all the parameters which controlling all these functionality. This is 3GPP parameters. You can find that there is something called discard timer. This is related to transmission buffer. We're speaking about that part. This is related to the sequence number, whether it's 18 bits or 12 bits, and header compression. It will be highlighting whether it's used or not used for uplink only. And in case if used for uplink only, by the way, as per the 3GPP, if used for uplink only, this means it will be only supporting profile 6. All the other profiles can not be supported, which is TCP/IP compression. Okay, so this is just a side note. And integrity reduction, also again, this is must for SRv1 and SRv2 cannot be disabled. That's why you find it here. It's under the data distributor. And you have out of the order derivative, we'll be discussing about that part. And these three parameters in between here, this is mainly for, again, A and C, not for 5G standalone. Then you have the T reordering and ciphering disabled. And let's move for each one of these functions, discuss it in more details. So the first thing I would like to discuss, if you remember the first function we mentioned about the BDCP buffer. Once the packet received from the TCP/IP or from the upper layer in general towards the BDCP, like assuming can be downlink or uplink direction, both have the same, you will find that once the packet received at the buffer, this packet, there will be a timer associated for each packet called the discard timer from the GNB side or from the U side. This can be configured for both of them, but you can check it from the drive test or layer 3 for uplink only. Downlink is already configured at the GNB side, and this is part of they call it flow control from GNB especially. So once the packet arrives, it will be starting this timer. So for example, assume that you have this timer is 1 second. So assume the packet arrived and it stayed in the buffer for more than 1 second. For example, it's being transmitted and somehow it's being failed within the air interface. For example, move to RLC and MAC. So it keeps, for example, doing retransmission, and it couldn't be, like, for example, couldn't be acknowledged by the other layers all that time. So the BDCP will not move it out of the buffer unless the packet is being acknowledged and transmitted from BDCP to lower layer and acknowledged from the lower layer. So assume that the packet is one second, and till 1 second, this packet is still there, or whatever packet is still there. This packet will be discarded after 1 second if it's not acknowledged again by the lower layer. And sometimes, as mentioned by 3GPP, if you read the description here, when the discard timer expires for the CBSDU or the successful delivery, see, these two things can discard the packet. Whether there is a discard timer expired for the BCP or the successful delivery being done. If the successful delivery being done, the packet will be discarded from BCP. It's not anymore needed in the buffer because it's already passed to the receiver side, so it can be discarded. But if it's unsuccessfully, for example, delivered and it's crossed the timer, then it will be completely discarded. But there is a side note and very important note you need to know. Okay, if you look into this note again from 3GPP here, let me zoom in just to have more clear example here. See, saying that sometimes the discarded packet will have already associated BDCP sequence number. Assume that you have packet number 3, packets with sequence number 3, and 1 and 2 being transmitted, and 4 as well. But only packet sequence number 3, it's transmitted to a lower layer, but it's not acknowledged. So in case if this one discarded because of the discard timer, assume the discard timer is very low, so this can cause a gap in your flow, right? Can cause gap in the sequence number. This means the receiver will be receiving sequence number 1, 2, and 4. So this 3 will be already discarded from BDCP layer. So this will be starting the T reordering at the receiver. So this might cause like a delay to the packet delivery from the BDCP to the layer. We'll be discussing about the reordering, but whenever you have out of order packet received at the receiver cannot forward these packets to other layer, which is TCP/IP. So this can cause a lot of, or a very high, for example, latency, especially if the reordering timer is very high, because within this reordering timer, the BDCP receiver will try to rearrange packets and send it in sequence to the upper layer. Okay, so this is just as a side. So yeah, so that's why here there is multiple consideration you need to consider. First of all, this timer should be very low, for example, to allow for example to allow leaf transmission if it's happening. to be completed. So it shouldn't be very low. It should be, for example, matching with RLC, especially for the uplink and even downlink, matching with the RLC transmission to allow, in case of the packet being retransmitted within the lower layer, to give it a chance to complete the retransmission before it's being discarded by the BDCB. Because if it's discarded, this means the packet is lost, or it's considered as a packet loss. And also from the upper layer here, this is like before going to TCP next session, there is also a retransmission timer. It's called RTO, but this it's like this timer have an initial value, then it will change dynamically based on different things I will be discussing in details. But assume that from the TCP itself, it having this RTO timer, usually the initial value was 1 second. This from TCP side, if the packet, any packet will be transmitted, it will start a timer called the retransmission timer, which is initially start as a first transmission with 1 second. So assume, for example, this packet, this timer here is 500 milliseconds. And during this 500 millisecond, the packet was not being acknowledged or not being transmitted. It stayed in the buffer. So this means it to be discarded. Once it's discarded, this means here it didn't like this means that TCP IP will even do the retransmission, because this already BDCB, this will be considered as packet loss, and this will be delivered to TCP that this packet is being discarded. So this will be early discarding for the packet. So usually, for example, we need to consider what is the, for example, let's assume this one is 1 second. So this, for example, can be 1 second as well to try to match it. This is just like a logical thinking, okay? This is the main consideration here. Let's move into the next function, but this was the first parameter and function which related to the BDCB buffer, okay? And BDCB buffer is being controlled by something called BDCB discard, and this is like under the flow control. And also the advantage of discarding the packet that sometimes you have a very high load in the network, so keeping the packets for very long time in the buffer, this can impact your capacity and load as well. So you need to have a kind of a compromise whenever you tune this timer between the retransmission and also the network load. Let's move forward and see what we have for the next function. Next part here, actually, this is related to the second part. If you remember, I was discussing about the BDCB header compression in general. I already discussed this one of my videos. You can refer to the VoLTE, for example, BDCB or robust header compression. It's exactly the same concept. It didn't change. I will quickly go through it, but if you would like to go through details, you can also check this video. So the header compression as well, it's optional. It can be enabled or disabled, as I mentioned in the very beginning. And usually this is like the main idea. It reduces the packet size. And reducing the packet size also can improve the capacity, and it also can improve the block error rate, because you will have more power per resource element. If you have less size of the packets, this means you can have more power per resource element. So here, the idea that of data compression, you can see that the compressor, the transmitter in general, will establish something called context, which is mentioned in the right here, or discussing here. Then the data, it will compress the data, then the data transmitted over the air interface will be like reduced. In general, the compression will like be reducing the number of bits transmitted over air interface. And this is usually especially for the small payloads, such as, for example, the voice over NR or VoLTE, or if you're speaking again voice over IP, and also for the TCP acknowledgement. We'll be discussing about the TCP in the TCP part, but there is a TCP acknowledgement. This is usually having a less payload. So the header, usually the header of the IP is accounting around 60% of the total payload. So assume that you have 60%. You can completely, for example, the IP header usually for IP version 4, IP version 6, which was going to be compressed. You can see that IP version 4 up to 60 bytes, usually 60 bytes, and IP version 6 is 40 bytes. If you do compress this one, this can go to only 3 bytes. So assume now if you have a low packets, this will be a very useful for that. So here the compressor like will be aligning with that transmitter with the receiver, like header compression with the compressing decompression functionality in the receiver. Here will be aligning this IP version 4 and 6 will be, for example, decompressed up to, will go reduced up to 1 or 3 bytes. And just as a high level again idea here, how this kind of working. Initially, the transmitter, if having kind of this bits, assume 21XX01, 21XX02. So the compressor or transmitter will understand that there is a context here. It can be removed. For example, it will take out the bits 21XX. This will be the context, and it will be just transmitting the last bit here, which is 1, 2, 3, 4, 5, 6. So this is how it's being decompressed. It will just initially pass the first one only to allow the decompressor or the receiver to understand what is the context. So it will allow the first one as it is, then it will again once establish the context, will just being transferring the last, for example, number here, as you can see. And this is how the out will be, and this is can reduce up like as you mentioned from, for example, 60 byte or 40 byte up to 1 to 3 byte, and this is very high compression ratio. It can go up to 70%, and this is very useful. Now let's move to the how to check the this kind of things from the parameters. Okay, if you look into here, there's two things you need to check. If, for example, if you are going to enable the feature for voice over NAR, or if you, or even for any other function, for example, like TCP/IP, you need to confirm two things. First of all, you need to verify whether the UE you are doing the test is supporting the compression or not, because sometimes the user itself will not be supporting this kind of robust compression. How to check that? You can through check the UE capability message from the RRC layer 3, and you will find under the UE capability message something called structure UNR capability, as mentioned here, BDCP parameters. This is all the profiles. For example, we have, as the 3GPP, we have from profile 0 till 4, as you can 104 here. You'll find all the profiles here. Here, all is false. This means this particular device is not supporting. So this is the first part you need to confirm. And from the layer 3 itself, if you zoom in here, RRC configuration message. Once, for example, you're doing a test and it's being supported, if you enable the feature, you need to confirm under the RRC configuration message as well. You will open, you'll find data review period being added. Here will identify your QFI, which is being XI, for example, and here it decided compression. For example, in this case, it will not use at all. It was like not used. Means that there is no header compression being used here. And in the bottom left example here, this is another one that's showing that it's being supported. As you look down here, for example, profile 1 and 2 is true, and this means that profile 1 and 2, which is used for voice over NAR, was being supported here for this particular message. This is how you can verify it from the drive test. Now let's go to the third function in details. The third function actually is quite known. You should be already aware about it, but it's fine. We can through it as well. This is related to the BDCP function in general, that it can do a split peer or routing or even duplication for the packets. But this is, again, it's mainly done in the non-standalone. So this is not related to standalone. And again, this is the bottom left parameters here. This can be again found from the RRC configuration. But again, this is mainly for uplink. Okay, especially for primary path and uplink that split threshold, and even for BDCP duplication. Because downlink will be already configured at GNB side. You can check from the GNB configuration. But from the uplink, the UE should know what he should do. For example, when he can start the uplink splitting, if it's going in the uplink direction. So for example, here, if you look into the BDCP here, the DCP layer and the downlink direction, it's having some threshold, internal threshold. It decide to do the data splitting. Okay, so how it will be moving? This is, for example, the 5G buffer at BDCP. It will split the data through the RLC entities for the 5G RLC. Again, this is BDCP for the 5G. It will be splitting the data, moving here. So it will be forwarding and splitting the data or routing the data towards different paths. For example, the first path, it's moving here from the 5G BDCP to 5G RLC. For example, assume this is the packets which should be transmitted. First 3 red for 5G, then the green one for 4G, as you can see here. 3 for 5G, then green one for 4G, and so on. This is how the packets should be transferred. So it will be transmitting first 3 packets here and 1 packet here. And here it will pass through this path, through the BDCP RLC buffer, then it will go through the air interface. And here it will pass through the X2 interface. Why this is important to understand? Because again, sometimes this can impact the reordering. For example, if you have a reordering, I will be explaining this part also next slides. But if you have reordering packets at the receiver, again, the BDCP receiver here, he will be waiting packets from 2 legs, right? So assume that there is a high delay in the 4G leg because, for example, 4G, let's assume speed is very low, okay, or having very bad performance. And also assume that the X2 itself having high delay. So this extra delay can delay this kind of green packets. This means at the receiver side, you will be receiving, assume this sequence number 0, 1, 2, 3, or 1, 2, 3, 4, okay? So the receiver will be receiving the red one, which is 1, 2, 3. 4 will not be receiving, he will receive 5. So the receiver will hold the data because of this reordering stuff until it having the complete sequence. So that's why sometimes it's critical to enable the data split, for example, for very high intersite distance. For example, if you have a neighbor site which is 4G only and you are enabling for this site as anchor layer and you're extending the coverage of 5G too much, this is can sometimes increase because the 4G will have a very poor performance and even the 5G as well, or any of the legs. So this can increase the delay of those packets. So accordingly, this is can do like kind of data stall, because at the end, the BDCV will not forward the packets to the upper layer until it have the correct sequence here. So this is you should be very smart when you try to tune the parameters in general, because again, this is can impact the user experience, the latency, and also sometimes it can make like kind of data stall. Okay, and this is again one important note. This is about the split period and routing. This is the functionality. There is also additional function called duplication. Sometimes can be configured that just to increase the diversity and increase the reliability. Sometimes the BTCP of the 5G will be transmitting the exact same packet through the two paths. So whatever packet will be arriving first, this will be successfully arrived. So this is giving a chance to increase the diversity in general, and this can increase the reliability as mentioned here. But again, it adds overhead. But the receiver, in general, the receiver, if received both packets from, because again, it will be duplicated packet moved from the 5G leg and 4G leg, if received at the BTCP or both of them, the receiver will be discarding the packets which is being added. But again, this is increasing the probability of having a much better performance, increasing reliability, and this can be, for example, advantage for the very poor edge areas where you know that, for example, particular area having a poor coverage and so on. So this was the function of the split peer and routing. And again, if you listening for each and single word from what I'm trying to say, you'll find that all these kind of things having a relation with timers end to end, because again, this is impacting sometimes the data delivery to the upper layers TCP. So this can still impact your end-to-end latency. So that's why sometimes if you did a trial, for example, for uplink direction, not downlink, to try to, for example, make it more difficult to attune to, for example, uplink data split threshold. This is the threshold, traffic threshold, where the UE will decide whether he need to do a split or not. For example, if the data and the buffer of the GNB or BDCP buffer crossing this threshold, any of those values you are setting, this means the UE will decide to do splitting. So assume that you are doing very early. So it's unnecessary. You're moving the data through two legs. This can again having a less performance, especially if you are in a very good area or good coverage. You don't need to do a splitting, because at the end, one leg can, for example, 5G can handle all the all the traffic, all the speed. So in this case, you don't need to do splitting to improve your latency, because again, moving towards two legs, especially the 4G and 5G, it will not be that good idea, especially in very good areas, especially also that you have, if you remember, especially if you're speaking about TDD for NR, you have, for example, the scheduling there is 0.5 millisecond, which is one slot, while the scheduling in 4G 1 millisecond. So again, this is increasing your delay. So this kind of things you can consider as well. Let's move forward to see the next function. Okay. If you were listening in details for whatever I was trying to say in all the previous slides, I was trying to align whatever I'm saying with this particular timer, which is a critical one. It's called BDCP reordering and in order delivery. The receiver in general, will try it all the time to make sure, depending on the parameter for sure. This is again, you have a parameter which is configuring that reordering, and even you can disable it. This is depend. Okay. But assume it's enabled now, and this is a parameter, and you are setting for this one of these values. This is the 3GB values. Okay, and this is reordering. It's at the at the receiver side. So here in the figure on the right here, I'm assuming the data is coming in the downlink direction from the UBF, assume from the application layer, till it reaches to the UE, which the UE is the receiver, okay? The receiver. So there will be a timer here called reordering. So let's see how this kind of working. Assume now you have the first packet being transmitted here called TCP sequence number 0 coming from UBF till the GNB here. So GNB BDCP layer. So again, if you remember, first thing the BDCP will do, it will be assigning a sequence number. Okay, this assigning sequence number 0. But by the way, those will be different, completely different compared to TCP. The BDCP will have its own sequence number. So I just give him a number to make it more simple to understand. For visualization point of view. But you will see next that it will have a different sequence number. Assume that BDCP is giving 0, 1, 3, and so on. So the the BDC will assign a sequence number to be able to allow the receiver to track the packets and also from the transmitter side. Then this packet successfully delivered from the GNB till the UE receiver has successfully received this packet. Then the second sequence coming from the TCP or from the TCP and upper layer towards it's coming with sequence number 100 from TCP, and it's allocated sequence number 1 from the TCP layer, and again it's reached till it reaches successfully to the UE. Then you have a third packet being transmitted, which is having 400 from TCP and sequence number 2 from the BDCB GNB side, from the transmitter side. This packet being lost actually. If you move here, this packet I consider is dropped. So it's being lost. Then the packet number 4 here is being transmitted, which is sequence number 3, and also transmitted till the UE RLC layer. So here what will happen, it will not be for the UE BDCB and RLC layer, this is the application, it will not be forwarded from the BDCB layer until this timer expires. See what happened. Once this sequence number 3 is being received here, because the UE was expecting to receive 012, so but he received 013 because this is out of sequence. So the UE at the receiver will start this kind of timer. It's called reordering, and this reordering will be starting, and it will be key. For example, assume it's 100 milliseconds. So once it's expired, in this case, time is expired here, it will be forwarding that part for the application layer out of sequence delivery. This means that TCP layer here will be receiving 0, 1, and 3. And by the way, the TCP having a capability of doing the reordering. If it's received the packets later on, back sequence number 2, it can do the reordering, and also the TCP can do something called selective acknowledgement, can do a retransmission based on timers, and have different things we discuss in details in the next session. But the case here that you can see, this is kind of delay accounted. Whatever packets is going to be transmitted, even 3, 4, 5, 6, 7, 8, all of that will be holding at the BDCB. It will never transmit it to the TCP layer or upper layer until this timer is being expired, until it allowed to move forward here. And assume this timer is very high. If this timer is very high, this means we are increasing the latency, okay? And also if this timer is very low, this can increase the probability of the receiver or TCP in general to do retransmission. And doing retransmission at the TCP, as will be explained later on, can decrease your throughput, because TCP have a mechanism whenever there is a packet loss or a packet considered as loss or even high latency. This can consider that the network have a congestion, so it can reduce something called the window size, so it can degrade your throughput. And if you look into the figure here, I quoted from this website. This is the same sequence. This is the same idea: sender and receiver. The receiver here, sender was sending 1, 2, 3, 4, 5, 6, 7, 8, 9. And this was going back, this packet was being received by receiver 1, 2, 3, but 2 and 8 was being derived out of sequence from the TCP side. This is assumed only for the TCP. So this can increase latency, reduce throughput, can do many things. So you should be very careful in general whenever you tune this timer. And you should consider this timer was, as I mentioned at the very beginning, was a discard timer. You should consider this timer was a TCP behavior. So you need to do a lot of tuning for uplink and downlink to confirm that this sequence, this timer is being set for appropriate value in your network. So again, this is very important. And by the way, again, if you remember in the previous session, this is an option. It can be even disabled. Or if you remember in the 4G itself, this timer was being set actually at the RLC layer. Now it's moved to the BDCP layer. But usually this, I will explain what kind of scenarios from high level perspective can trigger that package to be received out of sequence. I will explain to you, because sometimes you need not only to tune the timer, you need even to try to solve the root causes, which is causing this kind of out of sequence delivery within the radio perspective. So now let's move to the next function, which is related to when you disable this out of order, what will happen. Okay, if you look in this figure, this is exactly the same figure. It will be a very easy one. If you look down here first before moving to the call flow, there is, as per the 3GPP, there is a parameter called out of order delivery. You need to check in your vendor. It might be different naming or whatever, but this is the 3GPP name. If you find this one, out of order delivery, for example, if it's true, this means you are disabling, you are allowing the BDCP layer to just keep that the packets move out of order. If you read this sentence in the left here, in the case, for example, The out of order delivery flag can be used to specify that the receiving BDCP entity is not required to provide in sequence delivery of the higher layer. So if this one is used, this means the BDCP is not required to provide in sequence delivery. It will just deliver whatever it receives, despite it's in sequence or not in sequence. And for sure, can improve the latency, but again, this is also can cause multiple issues at the TCP, which is can retransmission increase, which is can impact your throughput in general. Okay, so this is would be exactly the same example as we highlighted: sequence number being transferred, sequence one being transferred, fine, two is being lost, and three is being sent here. But in that time, there is no timer being increased. In this time, what will happen? Just the UEBDCP receiver will be directly sending because there is no timer. It will be directly sending the packet without waiting for any particular time. And maybe later on, it will receive the sequence number two, and TCP can now make the reordering by itself, as will be discussed again in next session. This is out of order delivery. Now let's move to the last function of today about the BDCP. But before moving to the last function, this is actually I listed based on the logic. It's not based on the standards or based on documents, but I was just trying to think what kind of problems or issues in the RAN perspective can increase out of order. For example, receiving out of order. For example, assume you have a carrier aggregation. Okay, so this means you will have kind of two cells, two carriers. Let's assume one carrier was very low speed and the other was high speed, or one carrier was poor coverage and one was good coverage. So you will be receiving from those two carriers different packets, right? Each packet will have packet will be transmitted through to the different carriers with different sequence number. But once it's received the receiver, it might be received in a delay due to different latencies between the carriers. So again, tuning the carrier aggregation would be in that case you should be very careful not to tune it for keep it on all the time. You should be very careful as well because again this can increase the end-to-end latency. Again, dual connectivity as we discussed before, dual connectivity in general, same concept, 4G leg and 5G leg, maybe one of them having a problem, so this can cause also varying in the details. And RLC and HARQ transmission in general, bad radio condition, you will have one packet being lost in the air interface, and during the retransmission takes time until it's received to the receiver, so this will cause a sequence gap. Also with the flow control or the BDC discard as we mentioned, maybe the BDC discard uplink or downlink can make a discard if the time is very low. You can discard a packet which is already having associated sequence number, and if you discard that part, assume that what's already going there as retransmission or even discarded very early. In this case, this also can cause a gap in the sequence delivery, so can cause the reordering to be started. And also the X2 interface between the also in the NDC scenario, the X2, for example, is down or having problems or having a high delay or whatever, congested, whatever, can also increase the delay. So this can also reach into that you'll have out of order delivery. This is again something from my mind. You can maybe if you have other ideas, you can add it in the comments and share it with me in case you have other thinking or you have seen something from your experience. Let's move now to the last function as we discussed. This is actually the last one is very interesting. Again, if you're speaking about the user plane, especially for the acknowledgement mode, if you're speaking about the RSA acknowledgement mode, we have a retransmission mechanism starting from TCP using automatic repeat request, which is ARQ. You have a retransmission RLC, which is using automatic repeat request as well, and also you have the HARQ, hybrid automatic repeat request. But the three of them, TCP or RLC or HARQ, all of them can do a retransmission for a specific packet. If you have one packet being received, even specific segment being lost, it can make a retransmission only for that part. But BDCP is not doing this case. BDCP is completely different. And the BDCP retransmission is only happening in one case, okay? This case during the handover. Assume that your BDCP already established, your data being received at the BDCP, meaning that MAC is already flashed, RLC already established, and all the data is being delivered. But assume that you have moved from the source GNB B, for example, DU, to the target GNB B DU, okay? In this case, there will be a data in the buffer of the BDCP being there in GNB. It was being transmitted within the 4G, the source itself, but it was not yet being acknowledged by the lower layer. So this, once the handover is being done, there is no data forwarding from the source GNB DU to GNB DU, target GNB DU, because in this case, there is no actually interface between the GNB DU. If you read into as per the specific here, the specification, that there is no interface between the use. So in 5G architecture, you don't have a direct interface for forwarding the data. As a result, this is a responsibility from the DCP layer to do the data recovery. As per the 3GPP scope of the BTCP, I'll be sharing the source at the very end of this sessions. The BTCP do something called data recovery, which is retransmission. What will happen if you look into this flow during the handover? What will happen? The source GNB will forward something called downlink data delivery status from the source GNB DU to GNB CU, okay, the centralized unit. And it will tell him that I have some data which is unsuccessfully transmitted to downlink data DUE. So in this case, the GNet BCU will be requesting the BDCP to do the retransmission. So the BDCP data recovery will be started. So in this case, the DCP will support data recovery by retransmitting all the acknowledged BDCP data. It will completely, all the packets will be retransmitted. All the packets was not being acknowledged yet. It's unlike the, again, as I mentioned, the automatic reach request and the HARC mechanism, because both of them supporting the retransfer for a specific and developed packet, while this one will be just directly retransferred all the packets, and this is being needed for the lossless handover, because again this supports the handover scenario. And this was the last function of today's session. Next session will be starting with more dedicated for the TCP. TCP, to be honest, it requires like more than 10 hours or even more to cover it in details, but I will just try to give an overview of the most important parts related to the RAN perspective as well, what we need to consider for end-to-end, because at the end, if you don't have, at least don't have a high level understanding of the TCP and the end-to-end perspective, we might sometimes do action the RAN, which is not seen by the end-to-end, but can impact them. So if you understand, this will make it easy. So next session will be go through the TCP, then we'll be ending at the very end by the MAC layer, but the MAC layer will be more focused on the retransmission and how the retransmission is being working at the MAC, and also the aligning with other timers, which are already being discussed also during the RLC session. And also in next session, I will go through the more details about the interaction between TCP and BCP and even the lower layer. But usually you consider from TCP to BCP because TCP is the upper and BCP is the first lower layer here. So I hope if you like the session to share it and spread the word, and to press like and share, and see you next video. Thank you very much, and see you next session.